In this video, we solve problem 8.3.23-T from Essentials of Statistics 6th edition by Mario Triola. The problem statement says, assume that a simple random sample has been selected from a normally distributed population and test the given claim. Identify the null and alternative hypotheses, the test statistic, the p-value, and then state the final conclusion that addresses the original claim. Now, the problem statement says, a safety administration conducted crash tests of child booster seats for cars. Listed below are results from those tests with measurements given in HIC. That's how I'm going to pronounce it. Maybe it's pronounced HIC. I don't actually know. But those are standard head injury condition units. The safety requirement is that the HIC measurement should be less than 1,000 HIC. It says use a 0.01 significance level to test the claim that the sample is from the population with a mean that's less than 1,000 HIC. The question then says, do the results suggest that all of the child booster seats meet the specified requirement? So we actually have a really small sample size. We've got 1, 2, 3, 4, 5, 6 values. So this is something that you could do by hand. I wouldn't recommend doing this by hand. But I think we should do it by hand at least once so that we understand what the technology is doing for us when it computes the sample mean and sample standard deviation. So we're going to do this by hand, and then we're also going to use Excel to confirm our answers because that is actually the method that we'll be using when we have larger data sets, as we do in other homework problems. So first, let's state the null and alternative hypotheses. In order to do that, I'll share my paper with you. Okay, so we go to our problem statement, and if we were trying to identify the null and alternative hypotheses, we look for the claim. It says use the significance level to test the claim that the sample is from a population with a mean less than 1,000 HIC. So the claim is that the mean is less than 1,000. Now, since that does not contain the condition of equality, that means that that is the alternative hypothesis. And then the null hypothesis would look exactly the same, but it will have an equals sign there instead of that less than sign. So those are our null and alternative hypotheses. Let's go back to MyLab Statistics and choose that from the list. Okay, so I need the null to be that the mean is equal to 1,000 and the alternative to be that the mean is less than 1,000. Okay, so it looks like C is our option. Great. And then the next thing we want to compute is the test statistic. Now remember, whenever we're computing this test statistic, we're going to need the sample mean at a minimum and possibly the sample standard deviation as well. So again, I'll share my paper with you. All right, now let's look at the problem statement. It tells us what the safety requirement is. It gives us a significance level. And then they give us this sample with 6 values in it. And they tell us what the claim is that we're testing. But they don't give us any other information. Since there is no statement of that population standard deviation, we're going to use a student t-distribution here. Remember, the population standard deviation is represented by sigma. We'll use a student t-distribution, or we might say we are going to conduct a t-test. And the test statistic t in that case turns out to be equal to the sample mean minus the mean of the sampling distribution of the sample means divided by the standard deviation of those sample means. And it turns out that the mean of the sample means will be assumed to be the mean that's assumed in the null hypothesis. And this standard deviation of the sample means turns out to be the sample standard deviation for the particular sample we have divided by the square root of the sample size. Now, that's kind of a lot, but we will explore that more after we compute the statistics that we need to compute in order to use this formula. So we're going to need this X bar and we're going to need S. So that's the sample mean and the sample standard deviation for this sample that has 6 elements in it. So the first thing I would do is compute X bar. In order to compute X bar, if I'm doing this by hand, I need to add up all of the X's. So I just add these guys together. And then we divide by the sample size. So I'm going to take the sum of those and then I'll divide by 6. So the sum is 777 plus 767 plus 1,294. Well, that's bad. That's not meeting the safety requirement. Plus 694 plus 640 plus 478. And we get 4,650, and we want to divide that by 6. And so we get an X bar, a sample mean of 775. Okay, so that's what's going to go right here. Now we also need the sample standard deviation. Now it's been a while. I think we talked about this initially in chapter 3, but it turned out that if we wanted the sample standard deviation, what we would do is we'd take each X value and subtract the mean. And then in order to make these deviations from the mean positive, we took all of those and we squared them. And then we didn't divide by the sample size. When it came to the sample standard deviation and the sample variance, we always divided by the sample size minus 1, and that had something to do with the degrees of freedom. Now this is the sample variance. If I want the sample standard deviation, I take the square root of that. So what I need is the difference between each of these X bars and this mean squared, and then I need to add those together and divide by the sample size minus 1. So I'm just going to write all of that over here. I want X minus the mean squared, the sample mean, and the sample mean in our case is 775. So we'll have 777 minus 775 squared, 767 minus 775 squared, 1294 minus 775 squared, plus 694 minus 775 squared, plus 640 minus 775 squared, plus 478 minus 775 squared. Now I'm not actually going to do this arithmetic, not by hand. I think that's a little silly. I mean, it's a very good exercise for kiddos that are learning how to do arithmetic. But I think that we all already know how to do those basics. So we're going to add those guys together and then we'll divide by the sample size minus 1 and then take the square root. So I've got 777 minus 775, so we'll have 2 squared there, plus 767 minus 775 squared, plus 1294 minus 775 squared, plus 694 minus 775 squared, plus 640 minus 775 squared. So I think I missed an extra 7 there. Hope I didn't do that in any of the other ones. Let's go back and check. Looks like the other ones are fine. Hate that when we just type something in wrong. That happens, it's okay. So now we've got 640 plus 775 squared. And then I want to add this last one. I didn't do that one yet. So plus 478 minus 775 squared. And that equals that value. So I've got 382,424. We're dividing by the sample size minus 1. The sample size is 6, so we're going to divide by 5 and take the square root. So I'll just divide by 5, take the square root of the answer, and I get approximately 276.55885. So I think I'll round up to 4 decimal places. That's 276.5589. Approximately. Okay, so I've got my X bar and I've got my sample standard deviation. We should use technology, to check that as well. But before we do that, let's compute this using these values. And let's talk through what this formula means again. Okay, so we don't actually know the population standard deviation, but we know that we've got some sampling distribution of the sample means. And here we're assuming that the null is true. So that means that we're assuming that the true population mean is 1,000. Well, remember back when we studied sampling distributions, we said that X bar was an unbiased estimator of the population mean. So that just meant that the mean of the sample means is equal to the true population mean. And this time we're assuming that the population mean is 1,000. And so the question becomes, if the true sample, or if the true population mean is 1,000, is that 775, that X bar that we have in our sample, is that significantly low? If it is significantly low, we might say that's highly improbable that we would actually have that if this were truly the mean. So if it's improbable that it should happen, but it's happening, then maybe our assumption that led to us saying that it was improbable is false, which means that we should throw out that assumption about the mean, which means that we should reject the null hypothesis. So the question is this significantly high or low or not? Now, in order to determine whether that X bar is significantly high or low, we go to the student t distribution. So I'm going over here now. Now the student t distribution has a very similar shape to a standard normal distribution. It still has a mean of 0, but the standard deviation is greater than 1. It's going to be a little bit more spread out than a normal distribution. If I want to get from this X bar to the student t distribution with the appropriate number of degrees of freedom, I need to use this formula. So I'll substitute everything in now. X bar is 775. And we're just taking that, we're thinking of that as our random variable here, and we're subtracting the mean of the sample means. And the mean of the sample means is assumed to be 1,000. So that's what that is. And then the standard deviation of these sample means, the sample standard deviation of the sample means, is the sample standard deviation of our particular sample divided by the square root of the sample size. So that was approximately 276.5589, and then we're dividing by the square root of sample size, which is only 6. So all of this is an approximation, and that's going to give us a t value. Let's find out what that t value is. So we have 775 minus 1,000. Then we're dividing by this value right here, which is approximately 276.5589, divided by the square root of 6. Make sure you put those parentheses in the right place. Otherwise, due to order of operations, this will give you the wrong number. Even if it's right on your paper, if you type it in wrong, it's not going to give you the right value of that test statistic t. So hit equals or enter, and we get about negative 1.9928. Now that's not a number of standard deviations below the mean, but it's close to that. It's the t-score that is associated with that X bar. So this is our test statistic t, which is approximately negative 1.99. Let's go to my lab statistics and see if they like this answer. Okay, so we got negative 1.99. Oh, it's asking for 3 decimal places. I need my calculator again. You see that's negative 1.9928. So we should round to negative 1.993 if we want 3 decimal places there. Okay, great. And then the next thing it wants is a p-value. Now, if I want a p-value, I always have to think about the alternative hypothesis. I have to go back to this statement up here, and I have to think about whether the alternative is telling me that we care about being significantly low or significantly high, or if we really don't care, if we're significantly different from the mean, then we're fine. Our concern is being significantly low because of this less than sign. We can think of that as an arrow that's pointing to the left. So this is going to be a left-tailed test. Since it's a left-tailed test, what we want is the probability that our sample mean is less than this sample mean, given that the population mean is actually 1,000. And that turns out to be equal to the probability that the test statistic t is less than this value. So our p-value is this. So that's the probability that x bar is less than 775, which is equal to the probability that the test statistic t is less than approximately negative 1.993. And that is not a value that we have in a table. In order to find this p-value, we need to know something about which student t distribution we're talking about. The reason that we don't have a table summarizing all of these probabilities the way that we do with our standard normal distribution is every student t distribution is different. They are different for every sample size. So this is a student t distribution, but it corresponds to a student t distribution with a certain number of degrees of freedom. And the degrees of freedom is always given by that sample size minus 1. Or it is in this context, it's given by the sample size minus 1. There are other contexts when it will have a slightly different definition. But in this context, we've got sample size minus 1, and our sample size was 6. So 1 less than that is 5. So our degrees of freedom are 5 in this case. So the probability that our test statistic is less than this value can be found. We have to use technology, and we have to use this number of degrees of freedom. So if I want to find this, I'm going to show you how to use Excel to find this. You can also use TI-83 or 84 plus. You can use StatDisk, you can use Minitab, you can use lots of other software that is available. You could even just go to Google and search t-score, probability that t is less than this. If you just search for probabilities or p-values associated with t's, there are calculators online that will give this to you. But I want you to know how to do it using the technology that you have available while you're doing your homework, and hopefully everyone downloaded Excel because you have access to that as a TCC student. So if I want this probability, I'm going to use this function in Excel. It's t.dist. That's the one that I use if I have a left-tailed test. And then it asks for 2 inputs, 2 values of variables. You're going to put your test statistic right here. So that's approximately negative 1.993, and your degrees of freedom here. And this is for the left-tailed test. We have different functions for the right-tailed test and the two-tailed test. So I'm going to enter this in Excel and then see what it gives me for that p-value, which is the same as the area to the left. Okay, so now I'm in Excel, and I type equals t.dist. T.dist gives you area to the left. T.dist.2t is area in 2 tails. So if you give them a t-value and a number of degrees of freedom, it will give you the area in the tails beyond that on both sides. If you need a right-tailed test, just use the one that ends in RT for right. But for the left-tailed test, you just use that one. We want the t-value, so that's negative 1.993. And then the degrees of freedom, which is 5, and I forgot that other argument. And then they want to know, do you want cumulative area to the left or not? And we say, yes, we do. So we're going to say true. I need to put that on my sheet. Hit enter, and we find out that our probability of getting a t-score that is that extreme or more extreme than that is 0.0514275 approximately. Okay, so that means this area beyond that test statistic is about 0.0514275, and that's the same as the area beyond that X bar. Now let's go back to my lab statistics and see if it likes this p-value. It should. It was a left-tailed test, and we found the area to the left. All right, so the p-value, they're asking for it to 4 decimal places. So that's approximately 0.0514. All right, great, it likes it. And now that's enough for us to state the final conclusion that addresses the original claim. I'm going to do this on my piece of paper again, and then we'll come back and look at the options on my lab statistics. Okay, so if we're making a decision about a claim, we need to compare our p-value to the alpha value. Now, our alpha value is the value associated with our significance level. It's a significance level. So our significance level was given to us to be 0.01, and clearly the p-value is greater than alpha this time. So that means that even though this probability is low, so we've got a 5% chance almost, a little bit more than 5% chance of getting a sample mean that is equal to our sample mean or less than our sample mean. Well, it's not as low as the significance level that we have chosen for ourselves. It's not as low as that 1% chance. Since this is greater than the significance level that we're allowing ourselves with this test, we're going to say there's not sufficient evidence to warrant rejection. Well, there is not sufficient evidence to reject the null. So we're going to fail to reject the null. Okay, now we need to take this, failing to reject the null, and think about what that means for the original claim. So the null hypothesis in this case was that the mean was equal to 1,000. If we're failing to reject the null, what we're saying is the mean may equal 1,000. We can't reject it. We can't assume that it's true, but we don't have enough evidence to assume that it's not true. Well, if the mean may equal this and we're trying to prove that this is true, it looks like we don't have sufficient evidence to warrant support of this claim. So we'll say that there is not sufficient evidence to warrant support of the claim that the mean of the population that our sample was chosen from is less than 1,000 HIC. Okay, let's go to my lab statistics and choose the option that is consistent with this. All right, so we failed to reject the null. So we'll say there is not sufficient evidence, or there's insufficient evidence to support the claim. Okay. Then the last part of this question asks something else. It says, what do the results suggest about the child booster seats meeting the specified requirements? It says there's not strong evidence to suggest that the mean is less than 1,000 HIC. And one of the booster seats has a measurement that's greater than that. That's true. Let's look at the other option. The requirement is met since most sample measurements are less than 1,000 HIC. It's not. Even though that statement is true, it doesn't meet the specified requirement. Remember what the requirement is. The safety requirement is that the HIC measurement should be less than 1,000. Okay, and C, it says the test or the results are inconclusive regarding whether one of the booster seats could have a measurement that is greater than 1000 HIC. Certainly. And then part D says there is strong evidence that the mean is less than 1000 HIC, but one of the booster seats has a measurement that's greater than 1000 HIC. Well, there's not strong evidence that the mean is less than that. So it's not D. The only options that I think are appropriate here are A and C. A is true, but I don't know that it's telling me, it's answering the question that they're asking me. So let's look at that question again. It says, what do the results suggest about the booster child booster seats meeting the specified requirement? C says the results are inconclusive regarding whether one of the booster seats could have a measurement that's greater than 1000 HIC. I think that that's it. Because we're talking about the mean of the population these seats come from. Well, while the mean might tell us something about what we can expect most of the time, it doesn't talk about specific seats. If you are a parent buying one of these booster seats, you want to make sure that the booster seat your child is using is safe. And so we need every seat to meet that requirement, not just the average seat to meet that requirement. So I'm going to say that the results are inconclusive. Oh, review the results from the hypothesis test to determine the correct answer. Okay. All right, I guess it's part A, or the option is A then. So there's not strong evidence that the mean is less than 1000 HIC, that's true. And one of the booster seats has a measurement that is greater than 1000 HIC, that's also true. Okay, so A is true. But I think C is true as well because the results are inconclusive. That's not the answer that my lab statistics wants. So let's take that one. All right.